Hello guys, hope you're doing well. My name is Mahmoud Kiasari and today we are going to talk about one of the best chapters in advanced algebra, which we are going to touch vectors. So without further ado and without some kind of introduction, let's dive into that. So the very first thing that we have to know is that numbers are the ones that we were talking about it so far. Yes, we touched a little bit of coordinate plane and how we can show them, but we didn't actually touch the fact that rather than numbers, we do have another type of visualization, another type of formatting in numbers that rather than strange, they do have direction. This is something that we call as vector, and we are going to talk about it, why vectors are important and how we are going to somehow talk about them in detail in order to understand their characteristics. So let's talk about it. The very first question is that how we describe the concepts like force, velocity, or displacement that have both range as a number and direction. This is the time that we do have the vector. So for the introduction part, we had numbers and we called them as scalars. It means that those numbers were just actually numbers. They didn't have anything special. They were just numbers. We add them up. We do have something. We had mass. It was, for example, 70 kilogram. And for centuries, we've used just scalars. They were just numbers to measure how much. But there are so many other critical concepts and questions in science and engineering that you also have another thing in your head. Which way? So rather than just focusing on the range of the number itself, we need to focus on the direction. This is the time that vectors as an object comes in. It means that a vector is a simple object that packages both magnitude, it means that obviously how much of a range, and direction, which way together at a time. So we are going to talk about vectors in this chapter. So the two words of a vector, an arrow and a list of numbers. A vector, as we just talked about it, is a single idea with two perfect descriptions, and we are going to move between them constantly. So the very first thing, or the very first definition of vector is about algebraic view. It means that as a coordinate list. If you guys remember, for previous chapters, we had coordinate plane, and in coordinate plane, we had x and y. In x and y, by having 2 points, we could find anything or we could visualize them. But right now, we are going to move one step further, and we say that vector v, we can just call it as anything that we want, is an ordered list of numbers and its components. It means that in 2D view, right now, the thing that we know, I do have my vector as x and y. I will talk about it, what does it mean by x and y, by an example. In 3D condition, rather than just x and y as plane, we are going to have another subject, or we are going to have another direction that we call it as z, that we will talk about it in few slides. But let's look at the question. When we are talking about the vector and we say that 4 and 2, unlike the 4 and 2 normally that we have for algebra, that it was just a point, for example, this is 1 and 1 and this is another point, 4 and 2 in vector wise means that to go 4 units in the x in the positive or the x direction and 2 units in the y direction. Imagine that I do have a point and I would call it as 1 and 1. We can just call it as, for instance, y1. x1 and y1. Then by using the vector format of 4 and 2, we are going to move 4 to the right and 2 to the top. By having that, we are going to have a second point, x2 and y2. So by this concept, we somehow use algebra in vector itself and in the coordinate plane. Remember, a vector is not a point, unlike the fact that we had 1 and 1, 2 and 2, or any other pair of numbers that we consider as a point. Vector is not going to be a point. It's a displacement. It means that we are moving from one point to another. So remember about that. The coordinate of x and y are the instructions to this kind of movement for that specific displacement. They're not going to say that you do have a point as 4 and 2. No, this is the direction of displacement. Then we do have the geometric view. It means that arrow in a space. A vector is going to be an arrow, right? The arrow, like this one. This guy is an arrow with a specific length and orientation.
The good thing about that, the position of this guy doesn't matter. It doesn't matter if you have it like this, if you have it like that, if you have it over here. It doesn't matter. It's completely free vector. And this guy is going to representing displacement. Wherever you use that guy there, it means that whatever point that you have right now should move right to the left and 2 to the bottom itself, and we do have a new point. So let's talk about the Rosetta Stone. It means that how coordinates give an arrow a name. We are going to talk about small steps. That when we're talking about the displacement of 4 and 2, for instance, obviously we are talking about one step to the right and one step to the top. But actually we do have another format how we can show that one step to the right means what and one step to the top means what again. So we can talk about it right now. So at this point, a coordinate system is going to be the dictionary that translates between the geometric and algebraic world. Obviously, we do have the algebraic world that we only have numbers, and we do have a geometry that we are also talk about the direction. So at this point, how we can translate them together. So at this case, we do have just x and y axis, just like the thing that we know about the coordinate plane, are going to be defined by two special basis vectors. As I just told you, we are going to talk about one step to the right and one step to the top. This one step to the right is considered as I. Please do not confuse this guy with the I that we had with complex numbers. It's completely another factor. We are talking about vectors. Complex numbers are another dimension related to numbers, but these guys are just related to main numbers. So we are not going to move to hypothetical dimension. We are just working at the concept that we have, which is normal numbers. So I is going to be one step to the right and j is going to be one step to the top. It means that, for example, for the last one, if I would like to show that actually my 4 and 2 is about a vector, is about the displacement, instead of that, because I'm going to not get confused with the normal points that we have, 4 and 2 as a point, we can say that 4i plus 2j. Obviously, we cannot add these two because one is about x-axis, another one is about y-axis. So two unlike terms, or they're not going to be similar. Be careful about that. So we do have 4i plus 2j. At this point, I know 4i, or positive 4, step to the right and positive 2 to the top. So the algebraic form that we knew was 4 and 2. And it simply is going to be recipe right now. Take 4 steps in the I direction around the x-axis and 2 steps in the j direction. This is going to something that we call as a component form. That we can call it as 4i plus 2j. The coordinates are just the weights for our basic vectors. As you can see over here, I can be represented by this small vector, 1 only to the right is 1 and 0, and j can be represented by this 0 and 1. So the vector arrow is true object. The coordinates 4 and 2 are its description in one specific language, and the standards or the basis or the smallest step are going to be I and j over here. So let's talk about the combination vectors, because this is something important, the head to tail story of addition. To understand vector addition as a geometric composition of displacement, not just by using the formula. So imagine that I do have a case. There are two vectors that are going to start from the same position. I do have u and v. Obviously, they are not parallel, they are not perpendicular, so I do have u and v. And the question is simple, how I can add them up. Either I can move this guy, again, as I just told you, remember, vector is a free form. It doesn't have any specific position. The only thing that we can learn from the vector is that guy is going to displace one point to exactly another point. So whatever you have vector, you can move it wherever you want, but you still have to keep that specific shape. It is 4i plus 2j. You still have to keep that shape, and we are going to use that concept over here. What does that mean? Imagine that I would like to find a v plus u, and obviously it's going to be u plus v. So right now I have two ways. Either I can move this guy to the top and have something like that. Then when I'm moving from to this point, and after that I'm moving from this to this point, I can say that right now I do have a bigger vector that is going to do these two things with only one step. This guy is going to be u plus v. Maybe some of you would say that, is there another form? Yes, obviously. As I told you, instead of moving u to the top, I can move v to the bottom. So it means that at this point, I do have what? Sorry, I can move the v to the right. So at this point, v is going to be over here, and I do have something like this as v. Since I do have that, and what? I can move this guy to this one, still I do have the same vector. Remember that u plus v and v plus u are going to be the same. Everything is the same. The direction, the displacement, everything. Because at the end of the day, I have to keep the balance. So the formula is simple. The formula that we had actually was what? If u is u1 and u2, or u of u1 times I plus u2 times j, and if v is v1 and v2, again, it's about their x and y displacement. Then u plus v is going to be simple. u1 plus v1 is going to be what? My x displacement. And this guy is going to be my y displacement. This guy is going to be my I steps, and this guy is going to be my j steps. So we were talking about an analogy, and we were talking about the fact that v and plus u is going to be u plus v. So the simple act of adding components perfectly mirrors the geometric head-to-tail rule. As we were talking about it, we are going to move this guy to this section, or we are going to move this guy to this section. The second vector is going to start its position from the final step of previous vector. This is the way that we can do the addition, or we can do the subtraction. So the subtraction is simple. Instead of just having these two guys, as the way we had u plus v, for example, I would like to find u minus v. So what I have to first of all redraw the minus v. What is minus v is going to be like this. I don't have the space for that, but you get the concept. So this is going to be minus v, and right now I can find this u plus minus v. Still the same concept, and I'm going to reach to the thing that I like. The addition and subtraction almost the same. So what about the multiplication? About the stretching, shrinking, and flipping vectors. So multiplication of a vector by a scalar or a number is going to have effect over its size or its magnitude, something we know as a strange, or the number that is related to a specific vector is going to be strange or magnitude. So the only thing that would change what is your some kind of the magnitude itself. It means that 99% of the time it only has effect on its size. The direction is not going to be changed. Direction is going to be changed only at a point that you have negative sign. It means that your vector is going to be 180 degrees, or is going to be flipped, or is going to be backward. So at this point, imagine that I do have a vector, and this is my vector. Whatever is that. Oh, actually, we can find it, right? How many steps to the right? 1, 2, 3, 4, 5. So we would 5 to the right, and would be 2, 3 to the 1, 3 to the top. So I do have 5 and 3. So what would happen if I have the 1v? 1v means that just by itself. What about half of v? Half of v means that I do have a number, or I do have a scalar, and I would like to multiply by a whole vector. Remember that when we do have this kind of condition, your number should be multiplied by x displacement and y displacement at the same time. So I do have c times x, and I do have c times y. If you do that at this point, I do have half of v. 5 should be divided by 2, 3 should be divided by 2. So we do have something like this, and shrinking is happening. What about 2v? It means that at this point, my c is going to be 2. 2 times 5 is 10. 2 times 3 is going to be 6. 10 and 6. At another point, but I do have flipping. I do have negative of v. It means that everything is going to be changed. So one thing that I have to tell you at this point is, as you can see over here, maybe the direction would be changed a little bit, but it's completely based on your number. It is 2, it is 3, it is half, but at the end of the day, the direction is something that's not going to be changed that much. One important fact is about the direction is that direction can be changed, only your number is going to be negative, not just positive itself. So what about the linear combination? And we are going to build blocks out of everything. What does that mean? A linear combination of vectors u and v is any vector that can be written as a times u plus b times v, where a and b are going to be scalars. So the big idea over here is something we call it as a span. What is a span? Imagine I do have these two vectors, u and v. And a and b could be anything from the negative infinite to positive infinite, again scalar, and b could be anything from negative infinite to positive infinite. So right now we would like to find the span, or we would like to find the part that we consider everything, some kind of possibilities of a and b. So at this point, with just two of non-parallel vectors, it is important we are talking about non-parallel vectors like u and v, we can use the linear combination to describe every single vector in 2D space. Right now we are going to talk about the 2D. It means that we only have x1, y. The set of all of these possible linear combination of set of vectors is something we call as a span. For instance, if we do have these two vectors, we can call this side as its span, for instance. So the glimpse of future would be that this simple idea is going to be so helpful. We are going to use it in building complex vectors from a simple set, and it's going to be this kind of engineering is behind the computer graphics, data composition, and solving system of equation. You're not just going to learn that only talking about the vectors, but we are talking about the linear algebra. So span is the combination of vectors and linear algebra itself. So what about measuring a vector? How we can measure that? Well, the very first concept that we have to talk about, as we just mentioned, the vector has two things. The very first one is about direction, and the second one is about its magnitudes. It is strange, obviously. So by finding those, I can find everything related to my vector itself. So the very first one, which is about the magnitude, is simple. How we can find that? So if we assume that there is a vector by v, and I assume that this v is actually x displacement to the right and y displacement to the top, I can say that vector's component, x and y, and just the vector itself, right? This vector, they're going to form a right angle triangle. As you can see, the right angle means that one of the angles, one and only of the angles, is 90 degrees. We can find its length using a very famous formula theorem, Pythagorean theorem. What does that say? Pythagorean says that if I do have one side of my right triangle as A, and if I do have another side as B, and if I do have hypotenuse as C, my A to the power 2 plus B to the power 2 is going to be C2. As you can see over here, I do have all of the components related to vector. I do have x, I do have y. They're going to play as the role of a and b. Then I can finally find the c, or something we call as norm of v. What is the norm of v? Sometimes they showed it as this one, as an absolute value. It still means that the magnitude of that is specific. So the formula that we have, the norm that we can use it over here is going to be more v. Norm of v is going to be root of x to the plus y to the power 2. So we didn't use anything new. Actually, we considered the Pythagorean theory. So what is the physical meaning of that? It means that if a vector represents velocity, its magnitude is going to be speed. If it represents a force, its magnitude is going to be strength, and so on and so forth. So right now we found out how we can find the magnitude or norm of one specific vector. What about something we had, by the way, for about the direction or for about specific angle that we call it as theta over here. In the future slides, I'm going to talk about one thing, but maybe some of you would know about that, but we talked about a little about it in complex numbers. For the theta, we can just simply find tan inverse of b divided by a. And we have some rules about b and a. They could be in what vector. Actually, we talked about it in complex numbers. So you can find a video in our channel. So it's not that hard. It's going to be so simple. By you finding the delta, by theta, actually, you are going to find the specific direction that we need. Another important thing that we have to know is the concept of a unit vector. There are some times that we don't care about how big the strange or how big the magnitude is. The only thing that we care is about the direction. By just knowing A and B, what do we call it as unit? Because I do have a way that I can find, I can convert my vector to something that is going to show me the direction. In the meantime, or its magnitude is going to be 1. So maybe one of you say that, how exactly, and is it going to work for all of vectors? And I'm going to say that yes. So let's talk about this. The story is over here. A unit vector is any vector is a magnitude of exactly 1. And it's going to only represent the pure direction. And we are going to talk about it. So here's the process. This is something that we call it as normalization. Maybe some of you would hear that from other kind of courses. The normalization means that we are going to divide a specific number by a reference. And then by this way, we can somehow compare different units. For instance, if you're talking about electrical circuit, we can compare the voltage and current. We had something called it as per unit. It is not the concept over here. Maybe some of you would heard about that. So here's the process of normalization. Here's our goal. How we can turn any vector which has x, y, and 1 displacement into unit vector that points in the same direction. It means that I'm not changing anything rather than the magnitude. I still have to keep the direction itself. That is the important part. So here's the logic, and it's simple. Divide the vector by its own length. If you guys remember, when we found out some kind of the norm of v itself, it was a number, right? So if I divide that v or the whole vector itself by number, we know how we can do that. We have to divide the x and y or some kind of x steps and y step, both of them by the norm of v. And finally, I do have something we call as u hat, or I do have the normalized version of that specific number, or I do have the unit vector. So let's see an example. Let's start with a vector. Imagine I do have 3 and 4. Obviously, if I found the norm, it's not going to be what? 1. So what would happen if I would like to convert it to 1 and the only thing I care is about the direction itself? I can simply find the magnitude or the norm of that specific number or vector, then divide this vector, both of x and y part, by that norm itself. If I do that, I do have 3 over 5 and I do have 4 over 5. So this is going to be the shorter version of u, while it keeps this direction without worrying too much related to everything we had about the magnitude, because sometimes it's going to be big. So why it matters, why we like that? Because in physics and graphics, I mean something related to computer science or computer engineering, we often want to apply a force or light to specific strength with a specific strength in a certain direction. So we start with the unit direction vector and then scale it to the magnitude we need. It means that instead of just having the whole vector by itself, we are going to have the direction at the very beginning. We call it as unit vector because we know if we find the norm of that specific thing is going to be 1, and then we are going to apply the magnitude. We are going to make it bigger or make it smaller, whatever we can do with that. So let's talk about another thing, about the dot product, where geometry and algebra are going to collide. So at this point, we are going to see that how we can measure the alignment between two vectors. Are they pointing in similar, opposite, or perpendicular direction? So before knowing all of that, the very first thing that we have to know is that how we can multiply two vectors by themselves. I already know how I can add and subtract, but right now I would like to find something we call it as dot production. The dot production has two ways in order to find out. The very first one is about the normal calculation. U times V is going to be u1 times v1 plus u2 times v2. Again, finally, is going to give me another vector, right? So, I'm sorry, it is going to give me a scalar number. So right now, I found the dot, and I found the thing that I need. Another thing, or the meaning of that actually is this. U times v is going to be norm of u times norm of v, and finally times the cosine of theta. What is theta? Theta is the angle that you should find between u and v. It's not going to be related to x-axis anymore. It's an angle between u and v. So you can find it by what? Find the angle of v, for instance, if I call that theta v, and find the angle of u if I call that theta u, and that big theta is going to be theta u subtracted by theta v. Is that so? One thing that you have to know about cosine is some kind of FYI, is that cosine of theta u subtracted by theta v is most of the time that we are talking is going to be the same as cosine of theta v subtracted by theta u. So it doesn't matter which one comes first. You can use it. So the very first way that you had about the calculation is just simple, fast calculation, and you can find the result in the scalar point and not another vector. This is the good thing about that. On another hand, we do have another formula we just learned. So this formula is going to directly involve the length and the angle. The good thing is that right now we can find the angles, then talk about the angle between those vectors. It's going to measure of how much one vector goes in direction of another one. We were talking about the projectile, we're talking about specific thing in the future slide. That's why we care about that. So the key insight, these two formulas always should be the same results. If you find one of them not going to be the same as another one, you did something wrong. We can use it just for the easy algebraic calculation to discover the deep geometric truth. Cool. So let's talk about the geometry, because we were talking about angles, how we can find the angles. So finding angle between two vectors rather than just finding one at a time, just subtract them from themselves, can be done into another format. Something we call it as cosine of theta. Cosine of theta is going to be u times v in dot format that we just using algebraic calculation divided by norm of u times norm of v. Norm of u is something we know about that, root of x to the power 2 plus y to the power 2, the same concept with v. And right now I do have the cosine of theta. In order to find the theta itself, I do have cosine inverse of whatever that number is. So by this way, I can find a specific angle. The good thing we have that is that norm of v are going to be positive all the time. We don't care about that, right? But right now we care about one thing. If u and v are going to be positive, it means that if this dot production is going to be positive, it means that that angle is less than 90. If that u times v is going to be 0, means that for sure they are perpendicular. They are going to have the 90 degree between themselves. So this guy is going to be 0. If u and times v is going to be negative, I know for a fact that my angle should be more than 90 itself. For instance, about the perpendicular, in physics, if a force vector and a displacement vector are orthogonal, it means that the force does 0 work. It means that the dot product of f times d is going to tell us the whole story, right? So we just learned something about the angle and how we can use the sign in order to predict the condition. Let's talk about orthogonality and projection. So decomposition of vectors influence. So the very first, what is orthogonal, or what does it mean when we say that two vectors are actually perpendicular to each other? This is the special case. This special case says that if you do have two non-zero vectors, it means that u and v, there could be any number rather than 0, and those guys are orthogonal to each other, and only if their dot product is going to be 0. u1 times v1 plus u2 times v2 is going to be 0. There are some times that some of the vectors are anonymous. You don't have any idea what's going on. Rather than just drawing them and making sure they're going to be perpendicular or not, because you do have an idea that is going to be less than 90, is big or bigger than 90. You can find the dot production, and then by using that, you say that, I know for a fact that these two guys are perpendicular to each other or orthogonal because their dot production was 0 itself. So about the part 2, projection, the shadow analogy. What does it say? It says that, for instance, I do have a vector of v, and how much of a vector of v points in the direction of another u, or some kind of another vector that we call it as a u. Imagine that you do have your sun, and your sun shines what? Through your through your v vector. This is your v vector. I would like to find its shadow that it's going to show it that how much projection that I do have from v vector over u vector. As you can see, it has two parts. One big part like this, and another part which is perpendicular to this one. Let's talk about it. So actually, projection deconstructs a vector into two orthogonal parts. One part and another part, or both of them are orthogonal. One part is going to be parallel to a reference itself. This part is going to be parallel to a reference. If I assume that this guy, there's some kind of the u somehow is going to be my reference itself, this guy is going to be in parallel with it. It's right now, it doesn't show it that much, but this guy is going to be perpendicular to that. I'm sorry, this guy is going to be in parallel with your reference. One part is going to be parallel to your reference vector, and another part is going to be what? Perpendicular to that. So this guy, or v, is perpendicular to that. Why we use that? Because this is a mathematical tool in order to break down the forces into useful components. Gravity on a ramp. I will show you how we can actually apply this specific rule on real-world application. Or finding the closest point in a data set to a given line itself. So here's the idea, how I can find the projection, the formula and its meaning. Imagine that I do have my v over here, and then I do have u as my reference vector. Then I would like to find something like this. Projection of v over u, or the shadow of v over u. How I can find that? We do have two-step calculation. The step number 1 is find the scalar factor. What does that mean? It means that we need to know how much to scale the direction of u to get the projection vector. This scalar value can be found just using the dot production. The scalar factor of v over u, or the scalar factor related to projection of v over u, can be found using what? V times u divided by u, or norm of u to the power 2. This is a formula. So this guy tells how much of v is aligned with u adjusted to the one thing that we would like, the u's own length. It means that right now I do have my vector. This guy is going to be v, and it's going to find the alignment with the direction of u, and right now I can find a number for that, and I know the direction, and everything is okay. But not all the time my vector or projection is going to be over x-axis. Sometimes the u is over here, right? So right now, finding the projection of v over u, it is important. Is there any specific formula I can use? And I say yes. So at this point, instead of just doing everything that we had before, we can do this multiplication. V times U divided by U times U. By the way, when we say times, we are talking about vector multiplication or dotted multiplication times U itself. Right now, you do have a vector, you have the magnitude, and you do have your direction based on the displacement. Imagine that I do have a condition that these guys, let me just get rid of all of that, that I do have this condition and my V is 2 and 3. U is 4 and 4. And the question is that how I can find the projection of V over my U as the reference. So V times U is going to be 8 because it's 2 times 4, 3 times 0. Is that case? U times U is going to be 4 times 4, 0 times 0. It's going to be 16. Projection of V over U is going to be 8 divided by 16 is going to give you a scalar times 4 and 0. If you do that, you do have 2 and 0. So at this point, 2 and 0 is going to be this guy, right? As simple as that. It wasn't that hard. Everything was aligned to each other. So let's move from r to the power 2 or real numbers to the power 2 or two-dimensional word to three-dimensional words and see what it would happen. The very first thing that would happen in three-dimensional world, I do have much more freedom. It means that at this point, rather than x and y as my coordinate plane or my displacement, I do have another thing that I would call it as z. So at this point, I do have height. So height gives me this freedom to talk about the 3D objects, to talk about the actual objects that we do have around ourselves. So let's talk about in detail what's going on. So the robust abstract rules we're going to learn actually is not going to be changed. And that is a good part. It means that every rules really learned about the two-directional is going to be right about the three-direction. Again, what is the two-direction? It means that rather than x and y, as we had I and j steps, we are going to have a new concept. This new concept is something we call as k steps or z plane. So z is going to be a new direction. And from this moment, rather than just x and y, we are going to have another number as z. So let's talk about the rules. Let's talk about the details. So as I just told you, the only change we had is about the k and v is going to be like this. About the addition, we had u1 plus v1, u2 plus v2. The only thing that would change is instead of just u1, u2, we are going to have u3. v1 and v2, we do have v3, which is representing the z. So my addition is going to be like this. About the scalar multiplication, we are going to do the same concept, but at this point, we are going to have z to be multiplied by c. So c times x, c times y. At this point, we do have c times z. What about the magnitude? Still the same, but we do have another number actually gets in. And what about the dot product? Still the same concept with a new one. So here's about the challenge that we have related to visual. While we can still draw vectors in R3, and we do have another guy as z, visualizing sometimes becomes more complex. This is why this robust algebraic rules become even more important. So they work perfectly. In this kind of the rules that we have, they're going to work perfectly, even we can't easily draw that picture. As you just saw, right now we're only going to work with numbers. But about the way that we can visualize, and sometimes it could be a little bit challenging. But the good thing that we do have algebraic by our side, so we can use them. So what are the application of this one? The third dimension actually unlocks the ability to model the real work force, torque, and angular momentum. It means that we do have more access to 3D objects, 3D graphics and genes. For every game that you ever played, they're going to use this concept as we have. So let's talk about the real world application of vectors in action. The very important topic or subject that we do have vectors in it is about physics. Actually, vectors are not part of physics. Physics is vectors. It's everything related to vector. In physics, we are talking about the strange and we are talking about the direction. Imagine that we do have a displacement and D1 was 3 kilometers to the right or 3 kilometers to the east and D2 is 4 kilometers to the north. So we know something about that. It is 3 and 4. It is a vector. 3 has x-axis displacement and 4 has a y-axis displacement. So your total displacement is just simply the vector, the sum of D1 plus D2. And finally, is going to give you its magnitude, which is the distance that you had from the beginning. Simple as that. Then we do have the decomposing forces, as we were just talking about it, about using the projection through the specific reference. For instance, at this point, I do have force goes that way, but I would like to force that goes over this, that I would like to find a force because of gravity. So the only thing that I have to do, I have to project this guy over what? Over my reference itself, which is this one. We know a formula about that. So we are going to find the force pulling the box down to the ramp. It's something we know as gravity. We project the gravity vector onto the ramp, right? Simple as that. So finally, then another application would be work done by the force itself. Imagine that my force has an angle like this, and I do have D. So how I can find the amount of work? The work is going to be F dot D. So this F dot D, either I can use F1 times D1 plus F2 times D2, or I can simply use this norm of D times cosine of theta. We know formula about that? It's so simple. We can use it. That's why it's so applicable. You can use it wherever you want. So the idea of a vector and what comes next. Again, vectors are objects. They are not just lists of numbers or arrows. They are going to be fundamental objects that unite algebra and geometry. We talked about it. Then we had the operations. These operations are going to define the structures, addition and scalar multiplication, give vectors their life and create a vector space. We talked about it. Then we had the cosine of theta, or we had the dot product, is going to be a bridge between what? Between the algebra and geometry. It allows to calculate the geometric properties like length and angle using just simple arithmetic. So the very important concept is, if you cannot explain what a vector is, what vector addition means, and what the dot product does, you're actually not going to understand anything related to vectors. So guys, I have to emphasize on this part. Right now, we're talking about the algebra, advanced algebra, and we touched the point that we do have vectors. Vectors is everything. Yes, it's not somehow the algebra, purely algebra, but the backbone of vectors is going to be related to algebra. And you need that in order to expand your knowledge and use it for other concepts in physics, in the computer engineering, in electrical engineering, in almost everything. So it is so important for you guys to completely understand it. So right now, we just had a chapter related to that, probably, and I would make another video in order to have only questions related to this chapter, because I found that it is very important. But just in case, if you understand that you have any kind of questions related to a specific chapter, just comment me down below. I would be more than happy to help you. But if I couldn't do that, I'd probably make another video, or we can do it in another form. Again, thank you guys for being here today with me about this very interesting topic. I really enjoyed that, and I would be more than happy if you like, share, and comment this one and share it with others. It would be so helpful to me. My name is Mahmoud Kiasari. Have a super great day, night, whatever. See you around.